Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about inner product spaces. We'll begin with a refresher on the Euclidean dot product. I say Euclidean because it can be shown that all of Euclidean geometry descends from the dot product. In particular, let's let x1 to xn, y1 to yn, let these be elements of Rn. Then the dot product of these two things is the transpose of the first vector times the second vector. Now this is n by 1. Its transpose will be 1 by n times an n by 1 yields a 1 by 1. And so you end up with x1, y1 all the way down to xn, yn multiplied together and added up. In other words, the dot product of two vectors in Rn, usually denoted with a very conspicuous dot, is x transpose y. This is also why this is called an inner product, as opposed to the outer product. xy transpose. You can see that if I have xy times a b transpose, this is going to be 2 by 1, and that's going to be multiplied by 1 by 2. You'll end up with a 2 by 2. You'll have xy times a b, and that gives you ax bx ay by. In physics notation, they use the following notation for column vectors. This is called a ket. This notation is for rows. That's called a bra. And so you have the bra-ket notation. Now technically, in physics, in quantum physics in particular, these bras are normally not just transposes, but conjugate transposes as well. Not only do they convert the column into a row, they also take the complex conjugate of all of the entries. But if all of the entries are real, you get the same thing. With the bra-ket notation, when we write angle bracket x vertical bar y angle bracket, that is x transpose y, or conjugate transpose in the case of complex entries, which gives you the Euclidean dot product. There are certain properties of the dot product that you need to be aware of. First, if you dot a vector with itself, you can't get something negative, and the only way to get the dot product with itself to be 0 is if u is the 0 vector. The dot product is symmetric, meaning u dot v is v dot u. That's a kind of a commutative principle, if you will. once we introduce a new operation, we need to know how it works in relation to the other operations that we have, in particular with respect to scalar multiplication and vector addition. For scalar multiplication, scalar times the quantity u dot v is the same thing as associating that scalar with either of the factors in the product. And finally, u dot v plus w. Is there a distributive law? And the answer is yes. We're pointing out these four properties in one theorem because we're going to use these four properties to define what we mean more generally as an inner product. First of all, let's suppose that we have u, and it has coordinates x1 to xn. Then u dot u will be these coordinates times themselves added up. Now, because you're adding a bunch of squares, there's no way you can get a negative out of that. What is more, the only way you can get 0 is if every single term is 0, since they're all non-negative. And that's true if and only if u is, in fact, the 0 vector. On property 2, there's a simple proof of property 2. Let's suppose u dot v is u transpose v, which we know it to be. This is a real number. The transpose of a 1-by-1 matrix is itself. So u transpose v transpose is u transpose v. But distributing the transpose, remember it reverses the order. You get v transpose, u transpose transpose. And when you take a double transpose of a matrix, you get itself. And so we get v dot u. So u dot v is v dot u. The third property follows from the associative property of matrix multiplication. If I have A times u dot v, that's A times u transpose v, which is either A u transpose times v, which can be rewritten as AU transpose, or we can write it as U transpose AV. Either way, the property is proved. For property 4, if we take U dot V plus W, that is U transpose V plus W, which is U transpose V plus U transpose W, and that's U dot V plus U dot W, proving the theorem. Let U, with coordinates x1 through xn, be any element in Rn. We need a way of defining the length or magnitude of this vector. It's going to be called the Euclidean norm. First of all, it is denoted as follows. We have a double bar. Some texts use a single bar around the u, but that's confusing. It makes one think of the absolute value, which is not what we're doing here. We're dealing with the magnitude or length of a vector. And to find exactly how you would define the length of a vector, you'd square the coordinates, add them up, and take a square root. I should mention that there are other norms besides the Euclidean norm. This happens to be consistent with the notion of Euclidean lengths. Before getting too far into the properties, I would like to show that the Euclidean norm is the square root of the dot product of the vector with itself. This is more of an observation, really. If we take u dot u, that is x1 squared plus x2 squared to xn squared, which is the norm squared. The norm can't be negative because we use the principal square root in defining it. So when we take the square root, we don't need a plus or minus. It will always be the plus. That says the norm of u is, in fact, u dot u. Now, we do need a theorem about the properties of the norm. First, the Euclidean norm cannot give a negative value. Second, the Euclidean norm is zero if and only if you're dealing with the zero vector. The zero vector is the only vector that has length 0. The norm of a scalar times u is equal to the absolute value of the scalar times the norm of u. The effect on length of rescaling the vector is to multiply the length of the vector by the absolute value of. And also, the norm of u plus v is less than or equal to the norm of u plus the norm of v. This is called the Triangle Inequality. You'll see that this follows from a basic principle about triangles that you learned way back in high school geometry. In the proof, we can note that the norm of u is the principal square root of u dot u. This symbol, the radical symbol, is not any square root. If I hit this button on my calculator, plug in 4 and then hit that button, that's going to give me 2. It's not going to give me plus or minus 2. It's not going to give me the absolute value of 2. It's just going to give me 2. If I plug in 9, hit that button, it gives me positive 3. This is the principal square root. The principal square root is the non-negative one. So that proves property 1. For property 2, suppose 0 is the norm. The only way a square root can equal 0 is if the thing under it is 0. And we just showed that this is true if and only if u is the zero vector. So, the norm of a scalar times u, think of it this way. It's the square root of scalar u dot scalar u, which is the square root of scalar squared times u dot u. The square root can be broken up into two pieces, the square root of a squared and the square root of u dot u. What is the square root of a squared? You should know. The square root of x squared is not x. It's the absolute value of x. It can't give you a negative value even if x is negative. If I plug in negative 2 and square it, negative 2 squared is positive 4. Square root of that is positive 2, not negative 2. I get absolute value of x. I want you to take special note of that. Here I get the absolute value of a, and then the norm of u. On property 4, one way to view this is as follows. If you have u and v, we can make a side u plus v forming a triangle like this. One of the principles from high school geometry was that if you add up the lengths of any two legs of a triangle, what you get is greater than the length of the remaining leg. Now this is a strict inequality. How come when I wrote this property down before we had the conditional inequality with the possibility of equal to? That's because u and v don't have to form a triangle. And if they don't, you can get equality. So we have the norm of u plus v is less than or equal to the norm of u plus the norm of v. And that's based upon the high school geometry principle that when you add the lengths of any two sides of a triangle, what you get is greater than the length of the remaining side. I want you to take note that because the norm of a vector is the square root of the Euclidean dot product of the vector with itself, that our Euclidean notion of length descends from the Euclidean dot product. Perhaps if you have a formula that is similar but maybe uses a different kind of product, that will give rise to a different notion of length. So if we change from the Euclidean dot product to some other inner product, that we might end up with a different notion of length, and in fact you'll see that that's exactly true. So as far as we know, one of the most important aspects of geometry is the notion of length, and that descends from the Euclidean dot product. I claimed that all of Euclidean geometry descends from the dot product. What else do you need to do geometry but a notion of length and a notion of angle? We have the following theorem. If the angle between u and v is theta, then the cosine of that angle is u dot v over norm u, norm v. So our Euclidean notion of angle comes from a dot product and norms, but norms come from the dot product. It looks like our Euclidean notion of angle descends from the dot product as well. If we change to a different product, a different inner product, we'll get a different notion of angle, and hence a different geometry. To prove this, I want you to note that the norm of u minus v squared is u minus v dot u minus v. The dot product does distribute, and it is symmetric, so we can write this as u dot u minus twice u dot v plus v dot v. That is the norm of u squared plus the norm of v squared minus twice u dot v. Now, suppose this is u, this is v, and this is theta. Let's suppose that this is v minus u. The norm of v minus u and the norm of u minus v are the same. When you reverse the order of subtraction, you get a minus. But a minus inside of the norm goes away because scalars pull out in absolute value. So the absolute value of minus 1 is 1. I would like you to remember the law of cosines. Wasn't that c squared equals a squared plus b squared minus 2ab cosine theta? Aha, this is my c. The norm of v minus u is my c. I have c squared equals a squared plus b squared minus 2ab times the cosine of the angle theta. This must equal this, because we can cancel off the first couple terms, and after that cancel off the minus 2. We can solve for cosine theta equals u dot v over norm u, norm v, and that's it. If theta is pi over 2, then cosine of theta will be 0. If the angle between u and v is 90 degrees, then the cosine is 0, but that's u dot v over norm u norm v. And the only way a fraction equals 0 is if the top is 0. First, we make a definition. If the angle between u and v is 90 degrees, or pi over 2, we say that u and v are orthogonal. Yep, we don't say perpendicular, we say orthogonal. I guess the people doing this stuff weren't talking to the people using the word perpendicular. We have a notation. If u and v are orthogonal, we write u perp v. This symbol is called perp, and it stands for orthogonal. We have the Euclidean dot product. We have the Euclidean norm. There's also something called the Euclidean metric. First of all, it's denoted by d of u comma v, and defined by, this is to give the distance between the tips of the vectors u and v. So of course you take the norm of the difference. If you have u and v, to get that length of the distance between the tips, you take v minus u or u minus v. In this particular case, it's v minus u. It doesn't matter which way, because again, the negative can be eliminated. The length of that vector is equal to the Euclidean distance between them. Notice that if u is x1, y1, and v is x2, y2, then the Euclidean distance of u and v is the square root of x1 minus x2 quantity squared plus y1 minus y2 quantity squared. That's the usual Euclidean notion of distance in the plane. We could say that u and v are parallel if either of the following two conditions hold. U is a scalar times v, or v is a scalar times u. Yes, we are being a little cagey there. We're allowing for the possibility that one of these vectors is the zero vector. You see, if v is the zero vector, then there's no way u is going to be a scalar times the zero vector if u is not the zero vector. But it could still satisfy this condition. The zero vector is the zero scalar times u, even if u is not the zero vector. So while this doesn't hold, this one does hold. And the zero vector is parallel to every other vector. We write u is parallel to v in this case. U and v have the same direction if u equals a times v, where a is positive or 0, or v is a times u, a positive or 0. There is the following theorem. The norm of u plus v equals the norm of u plus the norm of v if and only if u and v have the same direction. This theorem goes in both directions, so we have to prove it in each way. We know that the norm of u plus v squared is u plus v dot u plus v, which is the norm of u squared plus twice u dot v plus the norm of v squared. Now, we said norm of u plus v. Now, according to our hypothesis, the norm of u plus v squared must then be norm of u plus norm of v squared, which is the norm of u squared plus twice norm of u norm of v plus the norm of v squared. That's true if and only if u dot v is the norm of u norm of v, and that implies, if and only if, u dot v over norm u norm v equals 1, but that's the cosine of the angle between them. The angle between two vectors can't be bigger than 180 degrees. It's always between 0 and 180 degrees, so that implies then that theta is 0 degrees or 0 radians. From this we deduce that they are a positive multiple of each other. To conduct the proof the other way around, let's suppose v is some scalar times u, where that scalar is bigger than or equal to 0. Let's look at the norm of u plus v squared. That's the norm of u plus au, which is the norm of 1 plus a times u. Now, 1 plus a must be non-negative because a is non-negative and we're adding 1. So when we bring it out, we must have 1 plus a times the norm of u. Scalars pull out from norms an absolute value, but we don't need an absolute value in this one. This is the norm of u plus a times the norm of u, which is the norm of u plus the norm of au, or the norm of u plus the norm of v. We're now going to talk about inner product spaces. Our experience with the Euclidean dot product was a warm-up to this more general concept. Let V be a vector space. An inner product on V is a function. It's usually denoted by an angle bracket, a comma, an angle bracket. It has two slots. It maps V cross V into the set of real numbers. We'll have a real inner product here. Sometimes they can be complex valued. We're not going to talk about that. Such that if u and v are elements of the vector space, then first, the inner product of u with u is non-negative. That's true for the Euclidean dot product as well. And the inner product of u with u is 0 if and only if u is the 0 vector. Second, the inner product of u and v is the inner product of v and u. Inner products are symmetric. Third, a scalar times the inner product of u and v is scalar times u and then v, or u and then scalar v. Scalar factors can be associated with either of the factors in the inner product. And finally, if I take the inner product of u and v plus w, I'll get the same thing as if I take the inner product of u and v plus the inner product of u and w. The same is true for the other coordinate. If we said u plus v and then w, the w would distribute, and that follows because of the symmetry. As you're about to find out, there are some rather unusual and interesting inner products. Of course, your prototypical example is the Euclidean dot product. Let me give you a different example. Let's take the inner product of two functions f and g to be the integral from 0 to 1 of f of x, g of x, dx. I'd like for you to see the similarities between this and the Euclidean dot product. Recall that if I have x1 through xn dotted with y1 through yn, what I get is the sum, as k goes from 1 to n, of xk, yk. Multiply the corresponding coordinates and add them up on this index k. In this case, the index are the x values, and there are clearly a whole continuum of those values. We multiply the outputs at the common x values, the common indices, but to add them up requires an integral. Let's look at a simple example. Suppose I have f of x equals e to the x and g of x equals x. Let's calculate the inner product of these two functions. According to this definition, that's the integral from 0 to 1 of x e to the x. What method do you use for integrating this? You only know 4 methods, really 2, but we'll say 4. Substitution, trigonometric substitution, integration by parts, and partial fractions. It looks like there's a part you'd rather differentiate than integrate. So this is an integration by parts problem. We'll use the tabular method. U is the thing you want to differentiate. dv is everything else. We'll differentiate down the first column until we get to 0. We'll integrate the second column. You multiply down diagonals and subtract. There's your integral. We'll plug in 1. When we plug in 1, we get e to the 1 minus e to the 1. And then we subtract what we get when we plug in 0, which is minus e to the 0. We end up with 1. There are other inner products that we could define. Let's suppose M is a symmetric matrix. Let M be n by n. Then I'll define the inner product of x and y, where I'm assuming that x and y are elements of Rn, to be x transpose M times y. I claim that this is an inner product, provided the matrix M is positive definite. A matrix M is positive definite if x transpose Mx is greater than or equal to 0 for all vectors x. And x transpose Mx equals 0 if and only if x is the 0 vector. Let's check the first property of an inner product. We'll take the inner product of x with x, which is x transpose Mx, and that's greater than or equal to 0, and equals 0 if and only if x is the 0 vectors. Also, if we take the transpose of the inner product of x and y, you get the same thing because the inner product outputs a real number, a scalar. But it's going to be x transpose my transpose. Remember that the transpose reverses the order in a product. We'll have y transpose, m transpose x, and m transpose is m. So we have y transpose mx, and that's the inner product of y and x. The other two properties follow just as simply. There are some interesting things you get if you start monkeying with this matrix M, making it something not necessarily positive definite. For instance, if M is the matrix -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, you end up with the special theory of relativity. Every inner product gives rise to a norm. The norm on an inner product space is the square root of the inner product of the vector with itself. Every norm gives rise to a metric. The distance between u and v is the norm of their difference. If a vector space has a metric, we call it a metric space. If a vector space has a norm, it is called a normed space or a normed linear space. If a vector space has an inner product, it's called an inner product space. Notice that every inner product space is a normed linear space, and every normed linear space is a metric space. The reverse is not necessarily true. There are metrics that do not come from a norm, and there are norms that do not come from an inner product. But we're taking the easy route, starting with an inner product. An inner product space is a vector space together with an inner product defined on that vector space. You know what it means for two vectors to be orthogonal. Their inner product is 0. What does it mean for a collection of vectors to be orthogonal? We'll say pairwise orthogonal if the inner product of vi and vj is 0 for all I not equal to j between 1 and k. As a little lemma, lemmas are like little baby theorems, we'll show that on any inner product space, the inner product of u and the 0 vector is the 0 scalar. The proof goes like this. We'll take the inner product of u and the 0 vector, which we know to be the inner product of u with 0 plus 0, 0 plus 0, 0, which is the inner product of u and 0 plus the inner product of u and 0 by the distributive property. Now every real number has an additive inverse. We'll add the additive inverse of the inner product of u and 0 to each side. But if I add something to its additive inverse, I get 0. And we can regroup on the right-hand side using the associative law and get 0 plus the inner product of u and 0. And hence, the theorem is true. Let's suppose that we have a collection of vectors v1 through vk Let's suppose these are pairwise orthogonal and non-zero. None of them is a zero vector. Then the set is linearly independent. So if vectors are all pointing in orthogonal directions, they have to be linearly independent. Let's prove this. Well, suppose 0 is c1v1 through ckvk. What we'll do is we'll take the inner product of the entire thing, c1v1 through ckvk, with vi for some I. Now remember, v1 is orthogonal to vi. The only one of these terms that will not give you 0 is the term involving vi, and that's going to give you ci times vi. But remember, vi is not the 0 vector, so the inner product with itself is not 0. So this is true if and only if ci is 0. But the I was arbitrary. The I we chose here was arbitrary. That means all the coefficients are 0. And if they're all 0, that means the vectors are linearly independent. We have as an immediate corollary v1, v2 through vn. If these are pairwise orthogonal, and non-zero in a vector space V, where the dimension of V is equal to the number of vectors in the list, then v1, v2 through vn form a basis for the vector space V. You know this because of the last theorem. If they're pairwise orthogonal, they're linearly independent. And if you have n linearly independent vectors in an n-dimensional vector space, then that does form a basis. The basis for some vector space V consisting of pairwise orthogonal vectors is called an orthogonal basis. If each vector in an orthogonal basis has norm 1, the basis is called an orthonormal basis. all of the vectors have been normalized, giving them length 1. It's an orthonormal basis. They're both orthogonal and normalized to have length 1. Of course, the classic orthonormal basis for R3 is I, which is 1, 0, 0, J, which is 0, 1, 0, and K, which is 0, 0, 1. Notice that if I have some vector x, which has coordinates x, y, and z, then x is the Euclidean dot product of the vector x with I. Y is x dot j, and z is x dot k. Notice also that we can rewrite this as follows. We can take x dot I times I plus x times j, the dot product, times j, plus x dot k times k to reconstruct the original vector x. This will work more generally with other inner products on other inner product spaces. We just better make sure that, like I, j, and k, it is an orthonormal basis. The theorem goes like this. If V1 to Vn is an orthonormal basis, on an inner product space V, and if you take anything out of that inner product space, you can decompose it as follows. You take the inner product of V with V1 times V1 and add up those inner products all the way down the line in exactly the same way as we did with I, j, and k in R3. To prove this, note that any vector V can be expressed as a linear combination of elements in a basis. Our job is to determine what the coefficients are. If we take the inner product of V with V, say, I, because V1 is orthogonal to Vi, when you take its inner product, you get 0. The only term that's left over is Ci inner product of Vi with Vi. But remember, the inner product of a vector with itself is its norm squared, and we've assumed that these vectors in the basis have been normalized, so their lengths are 1. We deduce then that the coefficient Ci is the inner product of V with Vi. Adding them all up, we get this. And that's it. Decomposing a vector into the form the inner product of V with V1, V1, and so on is like telling someone how to navigate streets in a city. Go this far in this direction, turn 90 degrees and go this far in another direction. That way you can go from here to here. What if the basis is not normalized? If this is orthogonal, but not orthonormal, then when we decompose the vectors, we still do the inner product, V with V1, we still get the V1, but we have to normalize things as we go along. V1, V1, V with Vn, 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 and then Vn. So this will work for general orthogonal bases. This idea of decomposing vectors into these orthogonal pieces is the basis for something called Fourier series. I'll show you that in the next section.